Hello, welcome to the show. My name's Relevant. This is Do All the Things. On today's episode, another noisemaker, another bell ringer, another tricky little circuit that I'm using to control this Proper Dingbell here so that I can use it as my doorbell, actually. Yeah. Stay tuned. Truth be told, this thing was already my doorbell. This is a kind of fire bell or something that I found in this abandoned logging camp all the way out in the middle of nowhere bush. Years later, it would get burnt down, so it was pretty clear nobody cared about this place anymore, and I salvaged this bell from it. So this is a little piece of vintage history. Well, maybe not history, but it's a Canadian-made Adaptabell, Edwards Adaptabell. It's rated for 3 volts, 60 cycles, 1.25 amps. It is an AC bell, so you give it an AC, and that's gonna make the hammer wobble back and forth to bang on that bell. That said, we can't just give it direct current and make it work, or can we? Well, I did make it work. It's been hooked up as my doorbell for a little bit of time now, because the circuit we have here, there's a base plate mounted to the wall. There's just a coil with a spring-loaded hammer in it. And initially, how it worked is I had this very rudimentary, well, there's a MOSFET in there, a scrap MOSFET, just making this very basic relay where the button would connect to the green wire and then you'd have power in and out in the red and black wires. And if you hit it with a certain polarity, you could pull the hammer back, tappy on the battery, there it goes. Now I've readjusted the mechanics in the bell. You can fine tune them with this screw here and this screw here and adjust the positioning of the hammer. And how I had it set up was when you gave it power, it would pull the hammer back against the spring. And then once you released power, the spring would send the hammer forward and ding the bell. So it worked purely off rebound. It did work. It was a little weak, you know, a little pink. Maybe if you're at the other side of the house, you couldn't hear it. And well, this worked all right for a while, except for, you know, if someone just booped the bell switch real quick, it didn't pull the hammer back enough and you'd get a really weak ding. And in theory, if you just pressed on that switch and held it down, you'd be holding that coil in a pulled back state and you could overload things. The readjustments I did pulled the hammer back away from the bell a little bit more, so now we need an actual AC signal to drive the hammer forward in order to ding it. I had to do that to correct the rebound so it would work properly with this circuit. So since I've been on a kick designing logic circuits and using, you know, things like MOSFET drivers, inverters, I decided to build a proper circuit to control it, to upgrade my doorbell circuit. Now I connect power to here, and now when I press the button, oh yeah, nice 3 clear dings. I could make it 1 ding. I could probably dial it into 2 dings. I could dial it into many more dings, but we'd start to overload the circuit because the duty, this circuit's very duty cycle dependent. So it's bad enough if someone came and spammed the bell. Yeah, you see here it's starting to get weak. And this chip here, oh, it got hot. Yeah. Okay, so it's not a perfect circuit. It's designed to be as simple as possible to get this job done with the assumption that someone's just gonna come up and just go like, boop. So we wanna make it so that they can just go, boop. And bam, the bell dings. Initially, I was running it off this 6-volt battery. That's not enough juice to run this circuit anymore, even though it's a 3-volt bell. Well, it is a coil. Coils don't necessarily have a set voltage. You can play with it a bit depending on your application. But I wanted to upgrade the power plant anyway. And I initially designed it to run off this guy. This was scrapped out of a VoIP box, and it's a perfectly good battery though. Though I might have other purposes for this, I actually have this crap here, which is almost half useless. My buddy got these off Amazon, I think, for dirt cheap. He gave me some, or he lent me some to try and then forgot about them, but they're such crap I don't think he cares about them anymore. It seemed like a good idea at the time. He was building RC and was experimenting with batteries. It's like, oh, 12,800 milliamp hours. Yeah, no. Anyone who knows anything about lithium ions knows that this is fake. I think I tested these and they're actually like 1,800. Well, they could even be 1,200. You know how it is. These knockoff batteries, they speak a big game, but really they're the weakest cells possible. Not even appropriate for RC because they're not going to be rated to put out that much current. They might have some sort of rudimentary protection circuit built in. I am not sure, though we will be treating them gingerly in this circuit. They have no problem delivering the current that this circuit needs, especially with a big reservoir capacitor that's really going to take up that inrush punch. Having no other reason to use these things, well, they're perfect for this, so I got a 4 battery holder for it, running about 15, 16 volts to this bell. But it doesn't seem to mind in a burst peak application like this. So how does this thing work? Okay, well, I'm glad you asked. I'm going to explain it to you now. Here is generally the schematic for it. And you can see there is a lot of these triangle symbols that have been becoming common in my circuits lately. We start off with our 12 to 16 volt input over here, going through a 4001 only because I have more of them than 4007s. Reverse polarity protection fills up this pre-reservoir capacitor. And then we have our one-shot trigger, buffer, whatever you want to call it, blast circuit. Transistors are voodoo that I don't quite fully understand yet. They're a bit weird and they let current flow through them all every which way. And in this case, we have this 10K pull-up resistor to the positive rail, which is going to hold the gate of this PNP closed. However, I do believe some of that positive is bleeding through the gate down here and charging up this capacitor, because this capacitor is indeed magically getting a charge even though there's nothing else connected to it. But then when we press this switch here and ground out the gate, it lets the charge of this capacitor blast through and trigger this circuit over here. And then the great thing about this is designed to be a one-shot. So even if I hold the button, I'm only going to get one actuation. That capacitor can't recharge until I let go of the button. And then it'll recharge in fairly short order so that I can do a couple presses easy. So this guy goes on and triggers this first buffer right here. Making an appearance once again is an IX604 chip. That is a MOSFET driver, 1 amp continuous rated, 4 amp peak, which is good because we're running peaks here. It's not working that hard, but it's great because we use it as a switching circuit. The one shot sends a positive signal to the input, so the output goes positive. Then through this feedback resistor, it feeds positive to the input. This guy latches on. The main power is directly connected to it, and then the output goes on to power the rest of the circuit. It's a great little thing we can do with MOSFET drivers up to a certain current threshold. Through this diode, to prevent the rest of the circuit from interacting with, its switching state, it goes on to power 74HC2G14 dual inverter through this 1K resistor pulled down with a 5.1 volt Zener diode. So we make sure this 74HC logic gets its 5 volts and that's it. And the Zener is actually very important here for reasons of consistency. This first guy here is going to be creating an oscillator to dictate what the hammer is going to be doing. When the output is high, it flows through this resistor here, charging up this capacitor. Eventually the input goes high, it inverts the output low, then it flows through this diode and then this resistor for a shorter duty cycle. So basically the high signal is pulling the hammer back, and then once the inverter swaps over, the low signal is driving it forward. So we have a longer pullback than we do drive forward. So it's kind of a slow with a quick punch. That gave me the best results, because the hammer is spring loaded. So we need a little bit more force to resist that spring. And then the spring's gonna start setting it forward. We just need a little bloop of that reverse phase to help things along. At which point we just want a nice little slap at a bell. Slap at a bell. We don't want to hold it on there. It's going to dampen it. We just want a nice little slap at a bell. Now that sends its signal out to an IXDD604 MOSFET driver. We're using another one of those IX MOSFET drivers here. They're great. They're handy to work with. Again, it has enough horsepower to drive the bell directly, provided we put a big wonking capacitor off of it. And it's funny because we have a capacitor here at the beginning, a capacitor here at the end. They're pretty much in parallel. We could kind of omit this capacitor, but it's good to have a capacitor close to the circuit that it's related to, especially playing around with these IXDDs. If you use them like this, where you're directly driving something of heavy load, they want capacitance as close to their pins as possible. It helps prevent voltage drops earlier in the circuit, which might cause instability in the logic. And it also makes sure that internally that has all the juice it needs to switch properly. MOSFETs, if you switch them as fast as possible, they'll work very efficient and won't generate any heat. But if this guy sees a voltage drop when it's trying to switch on, which it will because of the inrush current the bell's trying to suck through it, it's going to slow its on time and cause it to start to heat up and overload. I've gonna be honest, I've blown these things until I figured out, hey, I should put a capacitor right there, and then they love it. They work fine. The capacitor gives them the burst of current that they need to switch fast. So one of them's being controlled directly off the oscillator. The oscillator, the other half of the 2G, goes to this inverter, inverts it to go there. The other half of the DD to dictate the other phase of the bell. So this is basically an AC oscillator control circuit to run that bell. If we just gave it continuous power, we could just get a continuous bell ring. Brrring. Meanwhile, the IXDD has an enable-disable function, which I found was very important. I experimented with omitting it because the DD has an internal pull-up resistor, so it'll be enabled by default if you leave those pins floating. But every now and then, if the circuit went unstable for whatever reason, because these logics, they'll get positive cut off, but they might still have negative, and you know, this would try to feed current to the bell even without the oscillator doing stuff. And again, you can start to get an overload condition. So I found in this circuit, the enable function is very important. Now, for this to work the way I need it to, the DD is connected to the main power rail going all the way back to here, but the enable is connected to the switched rail coming off the DF. So the DF passes through this diode, powers this circuit, passes through that diode, enables the DD. These diodes are kind of important because they stop whatever's going on here from backfeeding. This has an internal pull-up resistor as mentioned, so it will backfeed positive through its enable pin, which will screw with this thing when you're trying to maintain an off state. So I have yet to explain the other half of the DF. Well, that's a timing circuit. So when this half of the DF goes high, starts powering this up, enabling, starts the dinging going, that high signal will pass up here. It'll go through this 1K resistor. It will get clamped to 5.1 volts for the same reasons why we have a Zener on the HC. Then it goes to this 91K that sets the timing, charging up this 10 UF. And then at some point, the input goes high, causing the output to go low. That sends a low signal to the input of the buffer, causing the output to go low, turning the circuit off. Once this output goes low, it can pass through this diode here, insta-resetting this timing circuit, making it ready for the next cycle. So that's basically what's happening here. The one shot turns on this buffer, that buffer powers the circuit, the oscillator fires up, starts oscillating, this gets enabled, that starts ringing the bell. In the meantime, we got a countdown timer on this inverter, which ends up pulling the input low and resetting the whole circuit, making the whole process just like that. So why do we have these Zeners? Now I could have used other logic for here, but the 74HC was convenient. I ultimately chose to go with this because having to clamp it to 5.1 to power this had the added benefit of no matter what voltage state my batteries are in, as long as it's well over 5 volts, this guy's going to oscillate at the same rate. In earlier versions of the circuit as I was developing it, I was running some circuits on here raw dog, and the oscillation and a number of bells would change with the battery voltage. If I went from the 15 volt to the 12 volt, it would change. And of course, batteries are going to run down over time, so it's going to cause your bell to change. And to top it all off, with less voltage means it takes longer for the timing circuits to cycle, so you would get more dings as the battery ran down. I didn't want that. So using 5 volt logic here solved that problem, and then that's why we have the 5.1 volt clamping here on this timing circuit. Even though this can run at full voltage, that's going to limit the amount of voltage that passes into the timing circuit so that the timing of this guy turning the circuit off, resetting it, is always the same. So as a consequence, I got 4 cells here. They're probably half run down by now. I'm getting about 15 volts. I get 3 dings. If I bump down to 3 cells, simulating a low battery state, I still get 3 dings. If I go to a 12 volt battery, if I decide to use this cell, I still get 3 dings. Consistent timing every time. Now, the only thing I don't like about this circuit is the pull-up resistor in the IXDD. I wish it didn't have that because that's the only source of parasitic drain that I've found in this circuit. You see, we have internally, I do believe it's a 220 or a 200K resistor to positive. And then in order to disable this, we need a pull-down resistor. It causes something in and around the range of 200 to 150 microamps of parasitic drain. And that's about as low as I could get this circuit to go. Say we use this big chunky 12 volt here. It's 7,000 milliamp hours, and we divide that by let's say 0.2 microamps. Well, that's 35,000 hours it would take for that thing to drain. Divide that by 24 hours in a day. That's 1,400 days. Divided by 365 days in a year. It's gonna take about 4 years to drain this battery. So if we did use this, and you maintain it properly, you're gonna charge it yearly or every couple of months, it would never be a problem. What about these weak ass friggin' puppers that are probably, we'll say 1,800 milliamp hours just to give them benefit of the doubt? It would take 9,000 hours, 375 days. Oh, these would be good for a year. Ultimately, this is what I'm going for right now because this is the most useless power system that I have. If it wasn't for that pull-up resistor, I've done experiments with these IX chips. In their off states, they use like almost immeasurable amounts of current. Logic can be good like that, using like 1 microamp to actually do the thing. So, what do we do with a drinking dingbell early in the evening? Well, we built this circuit. After much deliberation, here's what I came up with. I'm not gonna run you through this, it's the same as the schematic. Spec'd out for a 5x7 perf board. It's not the cutest circuit, it's a bit spread out, but it should do the job. I had a little bit more room to play with because it's going into this bulky enclosure here. But hey, without further ado, let's frickin' build on this thing, bud. And there it is in all its perf boarded glory. Done deal. It doesn't look as interesting assembled. Looks like there's a lot of room. I needed to have gapers here for the mount points. Underneath, you know, standard procedure. Weaving. Now the question on my mind is if we hook this up and test it, is it gonna work? As per my usual, I made these chips socketable. Now I don't expect the DF to fail under these circumstances, but the DD, she's working a little bit harder than maybe it was designed to. Again, as long as no one spams the bell too much, it shouldn't fry it, but hey, we have the ability to change it out if it fails. Now the question on my mind is if we hook it up and test it, is it gonna work? Okay, so how do we do this? We need to get, well, the bell wires are not in place, so we need some way to tap onto that. Just jamming into these holes, is that gonna stay put? Well, you can try electrifying it. There's general positive there, negative here. Oh, that did not feel promising. Wait, that was weird. It like stuck there. Inrush current, bud. Inrush current. Okay, let's get the bell hooked up. Actually, I got the phases wrong. Yellow's the bottom phase. Ho ho ho. Nothing suspicious so far. All we have to do is ground out this pin here. Just kind of have to short it out to ground right there. Oh yeah, bud. She works. Oh. I feel my finger here is on the DD chip and like it's cool right now, but then I'm gonna touch it. There's a blast of heat. It gets hot on one of those firings. Oh wow, it's working harder than I think it is, bud. It's rated for 4 amps peak. That bell's doing like 2 to 3 amps. But I don't know. That's interesting. That's interesting. It's gonna be interesting to see how long this circuit lasts, just like abusing those MOSFET drivers in this way. But so far in testing, it's been fine. Like, it gets hot, but these components, they're rated for like, what, like 125 Celsius before they melt? It's like computer processors. They can run at 90 degrees Celsius all day long. I suppose you could put a heatsink on there if you wanted to, but I don't think it's gonna be necessary. So for fabrication, I'm just gonna be installing these into one of these boxes here. That's your bog standard stove plug box. We're not gonna be needing this screw. We want it to sit right. And then I just have a blank panel that's just gonna like slip just on like that. And there should be enough room in there for this thing. I got to get this terminal strip mounted. Part number T38021-08-0. It is a terminal strip. It's got turrets at the back to solder to. It's got screws with little metal clamps underneath. That's going to bind all my wires. So technically I only need 6 connectors. I need power going in. I need a button connector. And then I need bell out. But I got 8 because I had 2 buttons. I might be daisy chain other circuits to this in the future, either the battery detector or I have another implement that I'm thinking of adding. I'm not sure yet. We'll see. But, well, I'm thinking something like button, common ground. There are 2 buttons. There's a front and back button. And initially I didn't realize I'd have clamps that I could put 2 wires into easily. Gonna need 2 for the bell, power in, power out, and a common ground. I do want to be able to pass power. And I'm gonna have this thing fused so that power out's gonna be post fuse. Before I do any of that, I gotta get this thing mounted. I gotta start plotting the course though. Maybe a screw hole like here, screw hole like here. And this steel is pretty skookum, or at least the last time I tried to work on it. Your bit's not gonna just blow right through it, that's for sure. Line up nice. Should be close enough. Once again, bust out Benchy boy. Make holes for my 632 screws. All pro tip, I just have like a magnet stuck to the machine and I just keep the chuck key on that magnet. On the other side though. All right, how are we looking here? Yes. They're nice enough to give us exact cutout dimensions on the data sheet. 375. You know, how about we do one of these? It was super not effective, except it got us a starting point. Starting point here, here. Then every 375 apparently. Except for these last 2 because of tolerances. Yeah, this hole's too far off. Okay, so now we just need to make holes that these can pass through effectively. Larger ones. 302 they're asking. But that depends on the tolerances here. They're a bit recessed, so like that won't touch if it's sitting right. 302 is what they're calling for, or 281. Either makes sense. How big of a hole is that? Oh, that's bigger than a 1/4 inch. Well, duh, that makes sense. Well, I guess we'll start with a 1/4 inch and ream out from there. Do I even have sizes on any of my cones for this? 307, 5/16. We might be reaming to 5/16 after. In the meantime, we got a whole frick ton of holes to drill, so let's get at her. Oh boy, anyone like chips? Alright, so how does this look now? Doesn't look completely straight, but it looks like everything's gonna clear just fine. Let's put some screws through there, actually fasten it down. Oh yeah, that'll be good like that. Nothing's touching nothing there. Nice. Starting to look more like an industrial implement by the minute. But now one of the most derpentine things that I did this whole process is I didn't pre-map the footprint of this board here. We need to make the 632 holes in it. Oh wow, is this bit dull or what? So this is generally gonna mount backside in some way, shape, or form like this. So we'll generally map out these holes. Oh wait, I need to use Mr. Dull Bit again because these are 632 holes. And I don't wanna, well, it worked in this machine. A little bit of forcefulness. Yeah, for some reason it can drill just fine in this machine. All right, now for the last piece. This is a Russian surplus fuse holder. I bought a bulk amount of these. Because of the nature of how this works, I feel fusing is good. If something fails, it's not gonna take out those lithium ion cells, especially cheap lithium ion cells. So assuming we clear this, it'll go somewhere around here. Alignment on this isn't critical, so we'll just kind of eyeball about where we want it right about. Phew. All right, let's use Mr. Delbit to pilot it. So we gotta do this thing where we make it quite a bit bigger because this is quite a bit bigger. 627 to be exact, or 15.9, 16 millimeters. What do we got? Either 17.3, whatever. Let's get it done. 4 steps. The one in big self-chamfering. How's that look now? Huh, huh. Bon. All right, let's get it all cleaned up and then, oh boy. I got chowder all over me. Huh. All right, I've gone ahead and got the wires pre-mounted to the designated wire mounting areas. That'd be generally right here for the negative bus. The positive bus, I have the terminal here, but it ended up somewhere along here. And then there is the trigger input and then bell outputs over here. I used a thicker wire, 20 gauge. I wanted something for, you know, power in and power out. I wanted to be able to move those amps easily. And then just green, yellow, 22 gauge for the trigger. So now we get to finally start fastening on this. Yes, the fun part. Got 1/2-inch standoffs. These things are great, these standoffs. Keystone 1451. A, B, C, D, and E are the size. Hopefully not too fussy about mixed metals. These are 632 1/4-inch stainless steel screws. Okay, just make sure we line this up relatively nice. Fasten it down with some kep nuts. Just plastic, bud, be gentle. Lettuce and tomato, get the fuse holder in place. This hole actually ended up being too big. That's okay, because there's a little widget there. Okay, looks pretty good. Let's get the circuit mounted. The only qualm that I have is I should have some form of ground to this plate, but I do not. So it's just a case of getting the final wiring done here. All right, well, the plan is button, button, solder them buttons. Then we're gonna have 2 common grounds. We'll put one here and then another one right here. The actual bell wires, and finally the power. We'll do a power in right here. Or no, that's gonna be power out. Aha, one more connection made to left. Made to left. What is wrong with your brain, bud? And that is going to be the proper power input. All right, this thing should be ready to go yet. I just want to quickly add last minute provisions for a ground plane here. Cause you know, if a wire comes loose and touches the plate, the fuse can't blow. You're supposed to make it so that your ground touches the metal enclosure. Now, I know I have a ground bus right up here. I'm just gonna quickly pop a line into here, solder her down, basically drag it across here. Just wanna make it even. There, now the kep nut can bite down on a piece of ground wire. Ta-da! Now if I sized everything up correctly, this should just plop right into here. Like that. And we have ourselves a bell driver. I'm gonna want to engage in some strategic placement of hot snot, even though we're not too worried about vibrations. Just kind of want to reinforce where the wires come out the board. And you know, make sure the nuts can't come loose. Probably should use Loctite for that. Put a dollop here, dollop there, dollop here, dollop. Why the hell did I just blow on the tip? And that should be good. And now, of course, we label it so that we know what's up. And future generations might know what's up too. You know, I worry that in the future, when I'm no longer around, someone moves into this house, it just scraps this nice work of art. Quite disappointing, the concept. But we got button, button. That's where we connect the button. There's a common ground. Bell, positive and negative. And power in goes directly to the fuse. Then from the fuse, power pass through into the circuit. So now if we go ahead and get our little dingbat back over there, we should be able to test on this effectively. So bell positive, bell negative. And I should just be able to secure these terminals right on here. All right, positive and negative. Now it's just a simple case of, yeah! And just in case you're wondering what the signature on this thing looks like. Oh boy. Pause. Our initial pull is about 200 milliseconds with a push of 16. Then our second pull, 112 milliseconds. Then again, a push of about 20. Then our second and third pull, 104 milliseconds. Again, a push of 20. That first 16 is a bit of fluke. And then it does like one last pull before the timer expires. But because of how the mechanics are calibrated, it doesn't actually hit. So the bell driver unit gets installed up into this general area of the house. Here's one part of the old bell. There was a buzzer on this too, and the bell would go bzz, ding. I gotta remove this old bell driver. Oh, it's just the bell driver enclosure, that is. I'm gonna slap a new one pretty much exactly where the old one was. Touch and do. Looks like one of the old screw holes will line up. Yes, indeed it does. Oh, the angle's not the best here, isn't it? Quick little pre-drilling for the new hole because that's how I like to roll. I get it in there. Couldn't be any easier than that, could it? Now this puffer should just slap in there. Yes. Oh, deforming a little bit with tightening, but it should be fine. All right, so the wires. Oh boy, I know this one's the bell. Oh, not enough room for the screwdriver, bud. Oh, careful, those screws are soft metal. Then this red one's power. Red is in, I got a whiff of marker on here, and it's labeled on the wall. So we want to put that on the input. And then finally the buttons. There are two of them. I'm only gonna hook up one for now. One's the front door, one's the back door, which is kind of silly. This one here is a bit twisted up. We do have one other bell connection, which is my test button here inside the house. We'll get that in the second lug. And we need to ground this. I guess we'll sneak it on with the main power. Here are the upstairs hallway. That's the mounting plate for the bell already installed, ready to go. It's just a case of getting the bell slapped back on there. And over here in the general fuse box room, I have this platform right here, and that's where I mount the battery. I have provisions for the big lead acid battery, but I'm not going to be using them today. This wire here comes in from the bell area, the power, and then I have this strap to keep a battery secure, and then this terminal strip to actually connect. It's funny, we got these tiny little wires here. So, pop the battery in, strap it down. Over and about where the bell wiring's installed, there's the absurd little test button. A little Morse code dealie, just kind of 3M taped to the wall. Oh, frick yeah, bud. I think it works. I heard that. Now that one particular button has the glitch where if you hold it and let it go, it dings twice. If you give it a quick boop, it dings once. I think it's just related to the fact that the button's so far away and, well, it's an old crappy button exposed to the elements. And finally, we shall give you video footage of bell itself go ding and... Uh-oh, I think I heard 4 dings there. Oh, I think there's a little bit of hammer bounce, bud. It's 3 dings for the most part. It should be good. It's a bit dark because I moved the light out, but hey, that's my new doorbell. Yeah, I made a YouTube video about me building and installing a doorbell. Isn't that? It just seems so, when you put it that way, it's like, why? Because circuits! That's why. I did it myself, DIY, logic, hacking, MOSFET drivers to do things they probably didn't intend them to do, and then bam, bell goes ding. So, I hope you enjoyed this. If you did, stay tuned, because sometimes I make bell go ding. Stay tuned, because sometimes I make bell go ding. I think that's the best one yet. Yeah.